students. Today let's discuss about pushdown automata. So far we have seen the DFA, NFA, epsilon NFA and all that. Today let's see this PDA. Before doing PDA, we need to know what is the limitation of DFA and NFA. Those automata do not have memory. At any one instance, if you want to know what is the input which you have read so far, you will not be able to say that. So that is the reason we go for this push down automata. So how does a PDA look like? Let's have a look at this diagram. This PDA has a finite state control to which we will be giving the input, and after processing the PDA will give us the output. The output is either accepted or rejected, and the addition here is a stack. So to the stack we are going to input or output the inputs. That is the addition in a PDA. Now after seeing the how to construct a PDA, let's see the formal definition of PDA. The formal definition of PDA goes like this. A PDA is a 7-tuple M equals Q sigma tau delta Q naught Z naught A, where Q is the set of finite states, sigma is the set of input alphabets, tau is the set of stack alphabets, delta is a transition function which is defined from Q cross sigma union epsilon cross tau to finite subset of Q cross sigma star. I'll show you some examples of delta later, how we get this function. And Q naught belongs to Q is a start state of the machine. Z naught belongs to tau. This is the initial symbol on stack A, or we can also say F. F, which is a subset of Q, it is the set of final states. Coming to the transition. The transition performed by the PDA depends on three things. One is the current state, the next input symbol, and the symbol on top of the stack. So in general, we are going to write the transition like this: delta of state comma input symbol comma stack symbol, which is equal to next state comma stack symbol. Now the action performed by the machine, it consists of certain things, that is changing the state from one state to another state and replacing the symbol on the stack. So we need to know certain terminologies before we design the actual PDA. One such is the move. So let's see what is the move of the machine. Let M equals Q sigma tau delta Q naught Z naught A be a PDA. The move of the machine is defined as delta of P comma A comma Z equal to Q comma alpha. That implies when the PDA is currently in state P, if the scanned input symbol is A and top of the stack is Z, then the PDA enters into the new state Q and pushes Z on top of the stack. The symbol on top of the stack and recently pushed symbol together is denoted by alpha. Here PQ belongs to capital Q, small a belongs to sigma, Z belongs to tau, and alpha belongs to sigma star. All this will have a clear idea when we start with the problems. Next definition you need to know is about ID, which is instantaneous description. It is just like a screenshot. The ID gives the current state of the PDA, the remaining string to be processed, and the entire contents of the stack. So how do we define this ID? Let M equals Q sigma tau delta Q naught Z naught A be a PDA. An ID is defined as a 3-tuple or triple Q W alpha, where Q is the current state, W is the string to be processed, alpha is current contents of the stack. So let's see, let the current configuration of the PDA is Q AW Z alpha, where Q is the current state, AW is the string to be processed, Z alpha is the current contents of the stack. Z is the topmost symbol on the stack. So let's take sample transition. If the transition defined is delta of Q comma A comma Z equal to P comma beta, then the new configuration obtained would be P comma W comma beta alpha. So the move from the current configuration to next configuration is given by this. Q comma AW comma Z alpha makes a move so to get P comma W comma B alpha. So by knowing the formal definition of PDA, the definition of move and the definition of ID, which is instantaneous description, let's see some of the sample transitions or of PDA. So the sample transition go like this. Delta of Q comma A comma Z naught equal to Q comma AZ naught. It means when we are in state Q, on accepting the input symbol A, when the top of the stack is Z naught, we will remain in state Q by pushing A onto the top of the stack. So this A would be the top of the stack. So let's see the second transition. Delta of Q comma A comma A. It means when we are in state Q, on reading the input symbol A, when the top of the stack is A, we remain in state Q and push A onto the stack. Look at the next transition. When we are in state Q, on reading the input B, when the top of the stack is A, change the state to P. Epsilon means pop the content of the stack. Now, look at the next transition. When we are in state Q, on reading the empty string, when the top of the stack is A, change the state to P, push A onto the stack. Look at the last transition. When we are in state Q, on reading the empty string, when the top of the stack is epsilon, change the state to P. So there are two things as I mentioned. The input is accepted by either the final state or the empty stack. If it is accepted by final state, the Z0 in the stack is retained. If it is accepted by the final state, then whatever Z0 is there, we will pop it off from the stack. So one transition for empty stack, one transition will be extra. So there is no change with the other transitions. We need to have one transition extra if at all the language has to be accepted by the empty stack. So that is about the introduction of PDA. So in the next video, let's see the problems. Thank you.